Zach loves the thrill of parkour. And if you're not familiar with that, that's this kind of sport, I guess you could call it, where a guy jumps around from the top of buildings to another top of building. It's kind of crazy if you ask me. Don't do it, or you might kill yourself. Anyway, he's trying to figure out how far apart a couple of buildings can be for him to be able to make a certain leap. He knows how much difference there is in height. He's jumping to a building that's 2 feet lower in height than the one he's jumping from. He also knows some information about his ability to jump because he recently tried out for a football tryout kind of thing, and so he knows he has a 3-foot vertical leap. He also knows that he can run a 5-second 40-yard dash. In that, he estimates that it's going to be about 7 yards for him to accelerate at a constant rate and then hold that speed for the remainder of the 40 yards. And based on that information, he thinks he'll be able to come up with what his top speed is as far as his running speed. He's going to jump across here, and he also notices there's this favorable wind that should actually help to push him across. And he wants to figure this up 2 different ways. One way where he actually accounts for that wind, and then the other way where he does not account for that wind. And if he accounts for the wind, he's going to give himself basically a 1 foot per second squared advantage of horizontal acceleration due to that wind. All right, so here's the steps that we're going to go through to help him figure out how far apart these buildings can be. Okay, so steps here. First of all, we're going to use the vertical leap. You're going to use that information to figure out what his initial velocity is when he jumps off of that building. So initial vertical velocity. Okay, and that's what he's going to use that information for, and that's the first step of our process. Because fundamentally, this is a projectile motion problem, and so to do a projectile motion problem, often what you need is some initial velocity data, and that's what we're trying to use this for, as well as the next one, which is to use the 40-yard dash data. We're going to use that to get initial horizontal velocity. Okay, and then lastly, after we've got those 2 things, then we can go into a computation for the projectile motion. And we'll do that for the case where there is no wind that you account for, as well as accounting for this extra 1 foot per second squared horizontal acceleration due to wind. All right, so let's go ahead and get started with this. The first step here, use the vertical leap. Okay. So for the vertical leap, let's just kind of draw a little picture of what's going on there. Here's ground level. And we're saying that there's an initial velocity whenever you do a leap like this. And this initial velocity, we'll call it Vy0. Okay, and after you have leaped, you travel up for a ways and then you start traveling back down. Okay, that whole way, if this is you, let's say you're treating yourself like a little particle there. If this is you, you have the acceleration due to gravity acting on you that whole way. And so we'll just say that's minus 32.2 foot per second squared. We didn't say this was on the Earth, but we can probably make that assumption, which means that we can take this acceleration due to gravity of 32.2 feet per second squared. All right, and what we know about this is that when he does this leap, he is able to get a 3-foot vertical, which means this is 3 feet from where he starts to where he ends up. All right, so that's the kind of a picture of what we're looking at there. We won't derive it completely from scratch, but we do have an equation that's in just about any dynamics textbook that you look at that allows you to relate velocities with positions when you are in a situation of constant acceleration. And this is what that equation looks like. It's basically your final velocity squared is going to be equal to your initial velocity squared plus 2 times that constant rate of acceleration times the difference between your end position and your starting position. Okay, and that's a very standard equation that is going to be given in just about any text that you would look at. Let's look at this equation for the case that we are dealing with here, like basically starting at, first of all, we'll say that we're starting at a point of origin, right? Let's just call that the origin. Okay, if that's the origin, then that means that this s sub naught right here is going to be 0 because we're starting at a height of 0. So that's one of the terms that we can get rid of. The other thing we can do is we will say up here at the apex of the leap, do we know anything else at that point? And we would basically say, well, we know that that apex is 3 foot high, right? So that is this s term right here. We also know that there's going to be 0 velocity when he reaches that apex, and that allows us to take this v that we have right here, which occurs, kind of at the end of the segment of time that we look at. We're saying that has to be 0 because there's 0 velocity at the apex. Okay? Once we do that, we actually can kind of simplify this equation down and say we can do this. We actually know s, we know a. What we want to know is what was that initial velocity. So let's solve for that initial velocity. So we'll say here that that initial velocity is going to be equal to the square root of minus 2 times a times s, where that s is that kind of final position. Okay, well, let's go ahead and plug in values for our particular case. So this is going to be the square root of minus 2 times minus 32.2 feet per second squared. Okay, and then that final position is 3 feet. Okay, and that's the calculation that we need to do. Real quick, before I do the calculation, let's look at our units. This ends up being feet squared per second squared. Since it's under the radical, that will end up giving us just feet per second. So that's good. We don't have to mess with the units at all. So take the square root. I'll just ignore those negating signs right there. 2 times 32.2 times 3. Okay, and this ends up telling me that I have 13.9, we'll say. V sub 0 is 13.9 feet per second. Okay, and if anyone's curious, feet per second is not a unit we deal with a whole lot. So let's just go ahead and I'll parenthetically put over here, this is about 9.5 miles per hour. That's sometimes a unit we can relate with, identify with a little bit more. It seems somewhat reasonable. All right, so that's step 1. We've got this initial velocity of 13.9 feet per second. Let me just make note of that right up here. 13.9 feet per second. Actually, additionally to that, let me go ahead and store this into, we'll just store it into variable a. Okay. What next? Well, the next thing we got to do is use our 40-yard dash data in order to come up with whatever our initial horizontal velocity is going to do. All right. So let me slide some of this down. And here I'm going to say 40-yard dash data. Just to help us understand it, let me actually plot what this data looks like. Okay. So what happens here, this is going to be time, this is going to be velocity. What happens here is that he accelerates at a constant rate. If you're accelerating at a constant rate, then that's a constant increase, or a straight line increase, we should say, of velocity. Okay? And so that's what we have in this little region right here, and then once he reaches his top speed, then he holds that top speed until the end of his run. Okay? So one of the things that we know here is that it takes him 5 seconds. So we'll go ahead and put that right here. This is at time 5 seconds where he finishes this 40-yard dash. What else do we know here? Well, what we're trying to look for is this maximum speed he is able to attain. So let me call that V max, because that's what we're actually looking for. Okay. One other thing we'll put on here real quick, and that is if I was to draw kind of a border around a particular area on this chart, we notice here that the area that we have, so area on our VT diagram or plot, is distance. Okay, the area under that V curve in the T space right there is going to be a distance. And so if I come up with an area enclosed that I'm showing right there, that area is going to be what? Okay, well, that area should be, just kind of put right here, that area is 40 yards. Okay. By that same token, we can take some different areas as well. Like I could take maybe an area right here, that little triangle, and I apologize, it's not tracking perfectly with it, but that, you know, the lines are, you get the idea though. The area of that little triangle right there will be how large? All right, well, the area of that triangle will be 7 yards, because that's the distance through which he had to run to get up to his top speed. Okay, so this area is 7 yards. Okay, we could also do another one if you wanted. So, you know, we could look at the area right here. Okay, that area would be what? Well, that area is just going to have to be the total area minus the other area. So this ends up telling you that that would be a 33-yard area. Okay, just by looking at how areas have to subtract. Okay. Well, one interesting thing here is it might be helpful for us to identify right here where this does the transition, that there is a time, let me just call it T sub A, right? There is this time where it transitions from where he's accelerating to where he stops accelerating. And that might help us come up with some equations that allow us to come up with Vmax based on what else we know about this chart. And let's do that by starting with the triangle. Okay, the formula for the area of a triangle is 1/2 base, and here the base, the width of that bottom of that triangle is just going to be equal TA, which we don't know what that is yet, times the height, which is Vmax. Okay, and what does this area have to be? Well, I just identified a second ago, that's got to be 7 yards. Okay. And let me leave that one alone for just a second, because right now it has 2 variables in it, neither of which we know. So let's kind of figure out where we're going next. It looks to me like maybe the next easiest thing to do is to look at this yellow rectangle right here and say that that 33 yards, okay, for a rectangle the area is just base times height, so that 33 yards is going to be equal to 5 seconds minus T sub A, Okay, and what's the height? The height is Vmax. All right, so this actually sets up a system of two equations and two unknowns. Since these are not linear, it's not a linear system because we have these two variables multiplied by each other. I think maybe the easiest thing to do in this case is to go ahead and do a substitution, which means I want to solve this Vmax, this equation right here actually for TA. I want it to come out with Vmax. So if I solve this for TA and do a substitution into the next one, that's a good way for me to get there. Okay, so this tells me here that TA is going to be equal to 2 times 7 yards divided by Vmax. Okay, once I get that, I can plug it in right there. And once I plug that in right there, I should be able to do some solving. Okay, so while I solve this, let me do one other thing as well. These units of yards are not consistent with the other units that I've been using here. Let me go ahead and get that converted to feet while I'm at it as well. So that means I'll have 33 yards, which let me multiply that by 3 feet per yard. Okay, that's the definition. A yard is 3 feet. All right, and this is going to be equal to 5 seconds minus TA, and I'm going to do this substitution at this point, 2 times 7 yards. Let me also do my conversion at this point, 3 feet per yard. And this divided by Vmax. Okay. That whole quantity is then multiplied by Vmax. All right. And that's an equation we can work with because it just has one variable in it. So let me go ahead and enter this, this equation. We'll start with 33 times 3. That will be set equal to the quantity 5 minus, okay, here we have a fraction, we have 2 times 7 times 3 divided by this variable. We'll just put x in for that variable. Okay, all this is going to then be multiplied by that variable again. This is the equation. We hit Shift Solve, and it tells us here that Vmax has to be 28.2. Let's think about those units for a second. Okay, Vmax 28.2. Okay, on the left we had feet. On the right we had 5 seconds minus 2 times feet over Vmax. Okay. And so since we're dealing with seconds, this has to end up in seconds inside of this parenthesis. And we had it in terms of feet. This should be feet per second. All right, and that is another good piece of information for us to have, because he's making the assumption that he's going to leap right at the edge of the building while he's running his maximum speed that he figured out from his football tryout. And he's also assuming he can achieve his maximum vertical leap. Okay, so the way we actually use this piece of information is to go up here and say his initial horizontal velocity now is 28.2 feet per second. So he's assuming whatever that terminal speed was that he was able to achieve in his football tryout, that's the same as he's going to be able to do when he jumps across the buildings. All right, so we are actually ready here. Oh, and there's a, again, it's always helpful to look at these speeds and see if it kind of makes sense. This is equivalent to about 19.2 miles per hour or so. Okay, does that kind of make sense? It seems to be reasonable to me. It's fast, but there are people who can run that fast. All right. So now what? we need to skip on ahead now to our projectile motion part of this problem. Okay, and again, it's often really nice to go ahead and draw a little graph of what you're talking about, kind of motion or you know, whatever it happens to be, whatever you're talking about with your problem. It's nice to make a little picture that shows what that is. Okay, and here's what he's doing. He's making a leap, and he's going to land somewhere. Okay, so he goes to this kind of final point. Okay, one of the things that we know about this is that relative to his starting point, it's going to drop here by 2 feet. So I'm actually going to call this y sub f. Y sub f is actually going to be equal to negative 2 feet. Okay, that's how far down he goes when he goes from his initial starting point, which we're making the assumption that starts at 0, 0. All right, he drops by 2 feet. Okay, what else do we know here? Well, let's go ahead and identify that we know what his components are of initial velocity right here at the very beginning. So the Vx naught, right, that is going to be equal to, that's horizontal, right, so it's 28.2 feet per second. Positive, because it goes in that rightward direction. Over here we have Vy naught, and this is going to be equal to 13.9 feet per second. And again, that is positive because it goes in that upward direction, which, unless we've done some sort of special definition about what direction we're taking to be positive, we would generally assume these would be our positive directions. All right, so we're done with that. Anything else that we need to know about this? Actually, probably one thing would be nice, and that is relative to our starting point. This is what we're trying to come up with, is our final x position, right? Okay, which we can put that in as x sub f. We don't know that yet. That's what we're trying to come up with. All right, for either of these, we can use a standard, again, constant acceleration type of formula. You'll notice here that regardless of whether or not he is accounting for wind, he's going to assume that he has a constant amount of acceleration in both directions. Okay? When you have a non-constant amount of acceleration, you can't just blindly use these formulas, but when you do have constant acceleration, you can use formulas such as, I believe it's equation 12.5. If you are using Hibbler's 14th edition, it's equation 12.5. It says that, let's say we have S is going to be equal to S naught plus V naught times T plus 1/2, again, constant acceleration A times T squared. That's kind of the basic equation. How do we plan to use it? Well, in the vertical direction, it doesn't matter whether or not we have the wind. The wind does not affect what acceleration happens in the vertical direction. So for that reason, we should be able to look at this path and say we can find how long it takes for him from his takeoff point to the point where he lands. How much time is that? And we can use an equation like this to calculate for that time. Here's how we do that. We know the final location in the y. So y sub f is going to be equal to our initial, y sub naught, I'll go ahead and write it out here, plus v, the velocity in the y direction at the beginning, times t. plus 1/2 of your acceleration in the y direction times t squared. That would be what the equation would be in the y direction for what we're dealing with. Okay, since we're starting at the origin, we can say y naught is actually equal to 0. Okay, for the rest of these, I don't think we can just get rid of them that easily. But we can plug in values for the things that we do know. So we know y sub f is going to be equal to minus 2 feet. That's going to be equal to our initial velocity here in the y direction, which is going to be 13.9, positive 13.9 foot per second velocity there. And then we have this times time, which is what we're trying to find, plus 1/2. Okay, what about our acceleration? Well, again, since this is on the Earth, acceleration on the Earth is assumed to be minus 32.2 feet per second squared. Okay, unless you're not at sea level, or you're given some other information about why it's not this standard value that we will typically use. All right, so we have that multiplied by t squared. Okay, and that's a little equation that we can then solve. You know, your calculator has a quadratic solver, but it also has just this normal solver for a single variable. So I'm going to just use that. We have minus 2 is equal to 13.9 times, okay, we'll use the variable x, plus half is just 0.5 times minus 32.2 times x squared. Okay, and that's my whole equation there. We're going to solve it, and what it tells us here is that this amount of time in flight that Zach experiences here is going to be 0.9, we'll just call it 0.989 seconds. Okay, that's actually not our complete, that's not our final answer that we have here. This is just a piece that we need in order to figure out how far he can go. Okay, the next piece is this. We want to look at, again, the same equation, but this time applied in the x direction. So xf is going to be equal to x naught plus v naught. I think I had, let's see, yeah, vx naught is the way I wrote that earlier, times t, plus 1/2 of ax times t squared. Okay, so this is in the x direction. All right, well, let's first of all do this for no wind. Okay, if we're looking at no wind, what we do is we say our final x position, we're again starting at the origin, x naught is 0, so we don't put that in. And then we put in vx naught, which is the same no matter what, that's 28.2 feet per second. Okay, times that time. Now we actually know what this time is. We put 0.989 seconds. Okay, plus 1/2 ax t squared. If we're not evaluating wind, how much acceleration do we have in the x direction? The answer is none. So this is actually as much as we need to do if we're trying to figure out the case of no wind. Okay, and that's actually pretty simple to do. We already have 0.989 stored in x, so all I got to do is take x and multiply it by 28.2. And that tells me how far you can jump. 27.9, we'll just say, feet. That's if he doesn't account for any wind helping him whatsoever. Well, maybe he's even more of a daredevil, maybe he wants to say, yeah, but the wind's actually going to help me out a little bit. So let's go ahead and deal with that situation. If we have the wind, then we say xf is going to be equal to, again, 28, so x naught doesn't change, but we will have the 28.2 feet per second. Okay, multiplied by 0.989 seconds. But to this, now that we have the wind, we can't say that AX is 0 anymore. And so we have to add to this 1/2 of 1 foot per second squared times 0.989 seconds squared. Now let's look at the units on here real quick. The first term winds up being in feet. The second term, you have feet per second squared, but then you have seconds squared over here, so that's also in feet. So we're good as far as that's concerned. Here what we'll do is we'll take x times 28.2 plus 0.5 times 1, I don't need to put that in there, times 0.989, which again is stored in the variable x still, squared. And that gives me 28.4 feet. Okay, so those are the answers to what he was trying to come up with. How far apart can the buildings be? Assuming all those assumptions, which are, that's a very daring thing to assume given that your life depends on it. But supposedly he should be able to jump across a 27.9 foot for the answer to that question. And the answer to this question, it'd be 28.4. All right. So thank you for watching, and if you enjoyed this video, you thought it was helpful, I'd appreciate it if you'd subscribe to my channel. Catch you on the next one.